All right, what is up, everyone? Welcome back to week 59 of Chill Kernel Hacking for Fun. I hope everyone is doing great. Today, we are getting right back into working on this network interface card driver. And I'm just going to jump right back into it. So we are focused on initialization. Let me just also... Before I jump right in, I'm just going to do my normal tests that the chat is working. Test 0, test Twitch. Yeah, all right. Initialization. So we are initializing the NIC, which involves doing all these things. And I was just kind of working on some very small details last week of getting just kind of basic functions for writing to memory mapped IO registers working. Just kind of as a sketch for how to do this. All right, looks like the chat widgets are working today. Nice. Okay. That's good stuff. So we have a couple of things we need to do to initialize the NIC. Also a quick test of my soundboard.
This is a certified hood classic.
All right, that should be working. So we have a couple things we need to do. Set allocate region for the descriptor list on a 16-byte boundary. That's what I did here. For the moment, I just made it a global variable. It's this array of descriptors aligned on a 16-byte boundary. And each descriptor is described by this structure. So we have an array of them. And I am somewhat arbitrarily choosing to have 32 descriptors. I think the max is 256. And I have no idea really what's a good size here. I'm just choosing 32. And then I have a big buffer that is the backing storage for basically all of the actual data that's going to be pointed to by the descriptors. Again, I don't really know what I'm doing. I just made it a page size, and I'm going to split that buffer evenly between each descriptor. Yes, and then we need to program some registers with the address of the region, and that's what I've done here. So we have the low and the high. I think these are actually 32 bits each. On this system, it's just, yeah, what's up, John? 2 essential soundboard sounds. Yeah, absolutely.
This is a certified hood classic.
And some applause, yeah. What's up, John? Hope you're doing well. Right, so we need to program some registers to point at the buffer. And that is what I've tried to do here. And notably, they need to be physical addresses. But we're not using 64-bit, so I just have the high register as 0, and then the low register is the physical address of this descriptor array. And then it's array, so I think I don't need the ampersand sign there. So that's the first thing. Number 2, set the length to the size in bytes of the descriptor ring. That's what I was doing here. TD len, right? And it's just the size, the total size of the descriptor ring. What's up, Kadar Codes? Welcome back. This register must be 128 byte aligned. Right, so I have I have 32 of these, and they are each, I believe, 16 bytes. Yes. Legacy transmit descriptor format 16 bytes. So 32 times 16 divided by 128 is 4. So that is a multiple of 4. Nice. Fixing the intonation on my guitar. Sick. I have no idea how to do that. Yeah, we should talk about guitar stuff sometime though, yeah. Right now I just have an acoustic guitar right here. Yeah. Afnan, dude, what's up? Good to see you with the test 1. All right. So yeah, size of that array. It's just a simple C array, so that should work. Next up, what is next up? Writing the head and the tail registers to 0. Software should write 0 to both to ensure this, right? And actually, the course description had kind of a hint about this. Note that the tail and the head, these are indexes into the array, not a byte offset. So I'm going to try to remember this so I don't screw it up later, although I might. And then kind of getting into these really annoying parts, actually. Setting a bunch of these bits on this control register. First 8-bit CPU emulator for general purpose register. Not a big thing. Definitely something. Nice, dude. First. Yeah. That's awesome. Writing emulators is a great way to play with this kind of low-level stuff, I think. That was how I started also. Okay, so now we need to set a bunch of bits in this control register, including the enable bits, some random stuff, collision threshold, and the really annoying part about doing this is that it's a bunch of stuff that's all packed into a single 32-bit word. And it's actually pretty annoying to do all those like bit operations. I was kind of trying to do them manually. Wait, I'm just going to actually copy and paste this whole thing. I already had it before, but I'll just paste it here. I was trying to do it manually with bit operations, but it's actually really annoying to set, this field is an actual number. It's like 4 bits or something like that. Let me see, the CT value, and this, no, it's like way more, it's like 8 bits. And it's sort of annoying to just like set that. So I'm gonna use a structure with bit fields, I think. So Meteor, how do you set up your learning process? It's very simple. My learning process is just following this coursework. So I don't plan it or anything. I just am doing the course and just letting that guide me. And then there's like this other register. So let's just do this. So set the head and tail, and then here is where I is it a public course? Yes, completely public. So I already have, what was I even doing here? Wait. Okay, I had some AI generated code actually. And I, okay, so here's my first attempt at doing this. I read the register and I was just trying to write back a bunch of things into it. But I actually think I need to do this. I will do this a bit differently. I think the original state of the register doesn't matter. I think it's okay to have it be all zeros, and we just set the things we need to. So, so basically what I want to do is make a structure with bit fields to describe this register, basically. And I kind of don't know how to do this, but I already was kind of asking AI how to do this. Yeah, and I think it kind of did it. It's 4, 8, 10, 4, and 8 or something weird like that. No, 6, no, 5 or 6. So here is what AI generated. Just curious. I actually kind of don't. I forget how to do it. These bit fields. And in particular, the ordering is always a bit confusing for me. I'm just going to ask, I'm still learning how to use Copilot also. When I do C structs with bit fields, what order do I need to make the members? I'm just going to ask it a very generic question like that. It's taking kind of a long time for a kind of simple question. I think it was doing this wrong. This is an interesting way to do it. So you have a value, you shift it into place, you AND the whole thing with the mask, and then you OR all of this together. I'm just gonna C bit fields in C. What order are C bit fields in? I kind of just want to write this declaration myself. What? BCC struct bit field order, like LSB maybe. I just want to. Maybe the easiest way to test this is with Godbolt. Okay. GCC struct x int main, and we're just going to have int a and give it 4 bits. I'll just have a couple of these. This is a super simple test. And then we'll just set x equal to 4 bits. So I'll set it to 15, or maybe hex f 0 0, right? And then include IO stream. Shit. I wanted to just, so if I then I just kind of wanted to print out the whole thing actually, but this is actually kind of annoying. What if I just do 2? And I casted this. So it's going to be yeah, right, just, yeah. Fuck, where do I see? Ah. Move 0 extend. I actually cannot read this. But yeah, it's just it is just ORing in 15 into EX. So I'm going to take this to mean that yeah, the first ones are the least significant. And if I would change this, we should see something different, maybe some shifting. How many hours of one spent in order to get good at this? I don't know, because I'm not good at this, apparently. So I'm just going to say that's enough of that and reorder this structure. So, so least significant bits are these. So basically, I think it generated it backwards. CT cold 4 8 10 4 6. Okay, so then that's sort of what I want, but Okay. So then I'm just going to, so struct tx control register, I'll just call it reg. Okay, so then, and what I want to do is what it says, which says the enable bit should be 1B. Okay, the enable bit is bit 1 of the control bits. So let's just start with that. Pad short packets, PSP is 1 also, which is bits. Which is bit 3. You know, I'm being kind of stupid. Right, okay, now what's next? Configure the CT to hex 10, which it's already doing. Ah, shit, did it? Bitfield should be little endian, I don't know. Until then, I'm guessing byteword doesn't apply with masked registers. Shit. All right, let's check out. Thank you for the link, John. Okay, right. Struct with some bit fields, and then you are just setting them to a bunch of values. Whoa. Okay, and RBP -4, -3, and minus, okay, that's kind of out of order. So the lowest one is hex 41. Then, so going up in memory, right, 41, then, yeah, okay, yeah. So that confirms that it's, yeah, lowest to greatest. Yeah. Thank you for the help there. Yeah, real noob hours with these bit fields. I never work with bit fields. Okay, what else are we doing here? So this cold, for full duplex. Do we have any guidance on the duplex? Duplex? Full duplex. Wait a sec. You can assume full duplex. Okay. Which means hex 40, which I think it was already there. And then any other bits? Not that I can see. Okay, what's next? Program. Okay, so that's pretty much it. So now I'm just going to do, I guess, what would this be? This would just be the address of reg, but casted to be a uint32t. And I probably need to make this packed. Can you make this packed? Why is it so slow? No, results, please define your input. Packed structs are what? It's somewhere here. It's like, I think it's attribute packed or something like this. Packed. God damn. Ah, is that really how it works? Struct underscore underscore packed. That compiled actually. Okay. Okay. So we are writing to the TCTL register. Guess we don't. It could be an anonymous struct too, I guess. Yeah. Hexalittles are big endian even on little endian platforms. Interesting. I've heard of that before. Okay, what? Wait, did I do something? Why was it? Okay, whatever. So we have that register, and then next up is the TIPG. To get the minimum legal inter-package gap. What is, okay, but the course has some guidance about this. Refer to the default in table. Don't use the values in the table in section 14.5. Refer to the default values described in table 1377 of section for the I. So I guess this means, do I need to look for another document? I think I do. All right. And it was saying what? 13.4 dot. No, wait. This cannot be it. This is a Word document. Okay, this is like not it. Interpretation number. Minimum legal. God damn. Not needed. Are not needed in full duplex, but are easier to always program values to the values shown. Okay, but maybe not. Maybe it's telling me to go to a different part of this document. Wait, 13. Jesus Christ, 13.4.34. Okay, I see. Okay, and what is it saying here? Table 13.7.7. Okay, cool. Refer to the default values described. Okay, what are the default values? What's up, Itum, Kali-chan? Like a prophecy, just think how cozy. How are you getting along? I'm good, but I'm struggling a lot. This is so detailed. Okay. So there are 3 fields in this register. And they need to be programmed to specific values. So maybe this is an opportunity for me to practice my bit field, my struct bit field programming. Okay. Struct tx tipg register shit x tipg register, and we have the 32t. It seems I already know this. Is that right? They're each 10 bits. Looks like it. Okay. And that's also okay, wait, what am I doing? The pact does not go here. The pact goes somewhere around here. I think. Right. Okay. We have this thing, and then we need to do a similar thing. Struct tg tx. The fields are automatically packed. Okay, cool. Good to know. I wasn't sure. I guess since, well, Okay, cool. Yeah, I guess I was a little bit unsure since these are multi-word. But like, that doesn't make any sense. So yeah, like it's uint32t, but this thing just describes 10 bits. So yeah, okay, cool, thanks. Okay, and what are the actual values we're going to put in here? Instruments to calculate value. To calculate the a value of 4 should be added as 4 clocks. The value that should be programmed is 10. I'm just gonna go with that, and I think that's what the AI was also generating also. The value that should be programmed is 8. Okay. For 1. And lastly, the value that should be programmed is 6. Okay. Default values as specified in okay, so we're going to do something very similar. Wait, am I doing this right? No, just this. Okay, and then this is going to TIPG. You know, I'm casting these to UN32. No, I think I'm missing something actually. I'm missing a bit field for the final padding, I think. To pad it to 32, right? Is that right? Yeah, there's 2 reserved bits, right? You can leave out the reserved field. Well, Interesting. Right, yeah, so you're saying to cast this to, like, get the pointer and then dereference it. Yeah. Okay. I see. I think I will still leave it in because it's just here in the spec. Yeah. Right. Do you not think it would simply work to cast this to UN32? I understand the suggestion, and I'm wondering if it would simply produce the same thing as casting the local variable. But there's a compile error, so maybe you're totally right. Invalid type conversion. Okay, I'm a bit surprised. I thought you could just cast stuff in C from arbitrary types, but maybe that's not true. Okay, and this thing is going to be TIPG. Right. Yeah. Right, okay. Cool, so there's that. What is next? I think that was it. Okay. What's up, Alone in the Dark? Greetings. Cool. Get the timer running. Let's just all take a quick 20 second stand up stretch. All right, be right back. According to C, converting pointer to integer is undefined behavior. I'm pretty sure what we've done so far is pretty legit. Okay, let's. Okay, we've done this part. What's next? What's up, Digitalized? Nice one. Good to see you. Okay, so So we basically just initialized some basic registers, and we have more to do. Use section 13 as a reference for the registers. Okay, no. Okay. Be mindful of the alignment requirements. Okay. It's a multiple of 8. Okay, don't use more than 64. Okay. So technically we have done this, but we're missing some pretty key parts because we haven't actually initialized the descriptors. Like we have this array of descriptors, but they are it's completely uninitialized. But maybe that's okay for right now. Maybe that's coming up next. Okay. So it says after you do this, try running QEMU. If you're using the core schema, you should see a TX disabled message when you set the TDT register, since this happens before you set EN and no further. Now that the transmit is initialized, you'll have to write the code to transmit a packet and make it accessible to user space via a system call. To transmit a packet, you have to add it to the tail, which means copying it into the next packet buffer and then updating the TDT to inform the card there's another packet there. It's an index. You need to detect if the queue is full, and there's some specific way you do this. And okay. And there's some considerations around this. But okay, it's saying just like try running this. So I guess we can try to do this. Let's just see what will happen. So basically all that is happening now is we enable, we PCI enable the device. We map the registers into memory, and we just call init. And then it's still panicking just to stop it there. So let's just run it. Okay, so we're not seeing any messages from QEMU, which this might suck. So I'm using the QEMU that I built. And I was pretty sure I enabled the, oh shit, that's the wrong. So, right, I was pretty sure I enabled the logging, because I just defined this thing. TX, so just check E1000. So, okay, so when we have this defined, this debug out thing becomes activated. And then it starts printing stuff depending on what has been enabled. Debug bit. And it seems like by default, only a couple things are enabled. So maybe I actually need to enable a lot more stuff here. For example, I feel like this should be on new lines to make this a bit easier. For example, I don't know, TX. I just want to see something. I'm just going to enable IO. Unknown. Oh, shit. Okay, it's compiling. Oh, what? Expected expression. So, oops. Okay. Does that work? I hope that works. Okay. Okay, so that built. So let's just see if anything different happens. Yes. Cool. Something happened. It said TX disabled and MMIO write, unknown write. That's bad. At address 410. Okay, that's good that at least that worked. Are there any other ones to enable? I don't know, maybe like IO? Takes error. RX error, I don't know. We're not using RX right now, but we might later. So, okay, cool. So, let's take a look. So it's saying takes error TX. You should see an E1000 TX disabled message when you set the TDT register. Interesting. I'm just going to, as a quick experiment, to check that that is working. I'm just going to comment things out. I'm just going to like, okay, this gets, what if I just commented all the stuff out, including the TDT, right? I would expect to not see either of those. Okay, we don't see either of them. We enable the TDT. And we get the TX disabled. And then what? Now we start, like some weird stuff starts to happen. Like that, so that one worked actually. And so this, is this the write that triggers that unknown MMIO? Yes, it seems to be. And we can actually see that because of the A, the hex A in the low bits there. Unknown write at address hex 410. So I am just using this header file that I copied from Kimu, which is 410. And I wonder if that, is that wrong somehow? Okay, I don't see anything mentioned here, so we can just quickly check the manual, maybe. No, it's hex 410, read and write. I'm glad I'm not doing the x86 version. This looks rough. Yeah, I mean, this actually isn't really x86 specific. This is just writing the driver for the Ethernet controller, or the network controller. And so even if you're doing the RISC-V version of this course, I think you would still have to do this stuff. Unknown right. Why? What could that possibly mean? So this comes from here. Size. Index. Okay. If index is less than num write ops and something something, do stuff. Else if it's less than the read ops, otherwise. And it prints out the index shifted to and the value. The value is just received here, the index. So it's given an adder which it masks and shifts over to, because each of these is aligned, it has like certain alignment. Then it has some kind of array of function pointers for handling all of these. And then it uses that to index into the array of function pointers. And then triggers some handler. And interestingly, it seems to not do anything on the read. It just triggers a debug output. So I'm not sure. Oh wait, no, but boy, this is the write function. So this is kind of odd. Okay. So clearly we're doing something kind of strange. Unknown write at address 410. So it shifts it back to get back to the actual offset, like the actual byte offset from the base address, in order to print it here. So maybe what that means is that is not implemented by Kimu. Because that would be so annoying if that was the case, because we spent a bunch of time trying to figure out how to do that. And in the end, the AI did it anyway. But maybe it's possible that all these TIPG things are completely unimplemented, because it's like some weird hardware, very specific hardware thing. I'm just going to assume that's the case, which is annoying, but okay. I'm just going to comment this out. Okay. A manual says to do this, but Kimu doesn't implement this MMIO. That's annoying, but so we're just going to move on. What's up, AAAB? And also, what's up, VPool? Hype up. Hey, Mark, thank you. All right. So I needed a lot of help from that, thanks to John and everyone else, but we got our first TX disabled message going, and I sort of think this is approximately working. Okay. You know what, I'm going to go back to fork. Okay, so do not need this. a function, this thing's there. Delete this. Okay. Now I'm going to break this into a few commits. I'm going to add import headers from 1000 headers from Kimu. Right, okay. And it's just going to be a whip of implement basic nick initialization. Okay. So what's next? So there's all this stuff it says about how apparently we might be ready to transmit a packet soon. Apparently the nick is initialized. And no further with this. I just am curious where this message, tx disabled. Okay, so it simply just, it apparently was about to do a transmit, but it just checks if the thing is enabled or not. And here, when you write to the tail register, apparently that actually triggers this thing to transmit in response to that. But we don't enable the nick until later. So at this current moment, nothing happens and we see the print. So I think I completely understand that. Okay. Next up. I'm just gonna copy all of this. This all seems important. Next up is to do this. Okay. Write a function to transmit a packet by checking that the next descriptor is free. Copying the data. Copying the packet data into the next descriptor and updating TDT. Make sure you handle the transmit queue being full. Okay. At one point it also said that updating TDT was kind of tricky or something. Correctly updating the tail register without confusing the E1000 is tricky, be careful. Okay, I am not sure what it meant by this. Maybe it's talking about how things are, like, it's not a byte offset, it's a index offset. Okay, so write a function to transmit a packet by checking that the next descriptor is free. Sup, Sam, where did you learn this? I am learning this right now on the spot. Live on the internet, which is why I'm kind of sucking. But in general, I've just been learning this by like streaming myself being stupid for a year. Yeah. Okay. So I am going to make a function called something like E1000 transmit, for example, and we will fill in stuff as we go. We're going to need to take a pointer to some data and a size for, I don't know, len, and it's generating all our code for us. Can I like disable Copilot temporarily until I need it or something? Configure code completions. I mean, it was actually very useful, and maybe it's just best for me to keep it on. So we have a buffer, and we will also just take a driver as the argument. I don't know, to avoid too much global variable stuff happening. I mean, the only thing in the object right now. Barack Obama says, extensions copilot, disable inline suggestions. Thank you. Disable inline suggestions. And then is there a way disable inline suggestions? Mentions copilot. Rename. I don't completely see that. All right. Okay. Checking that the next descriptor is free, copying the data and updating TDT. Okay, I'm just gonna check next descriptor is free, copy packet data into descriptor buffer, update TDT. Right. Handle the transmit queue being full. But time for a quick 20-second break to stand up and stretch. Oops. All right. Handle the transmit queue being full. Okay. So yeah, basically the first thing we need to do is check if there is a free slot for us. What's up? Hey Omar, finishing recent. Considering starting the same course, what free bucks do you think are good? You need to be pretty solid in C, first of all. And just in general, kind of working with compilers and debugging build errors, especially. I would say those are some of the main things. But I mean, just try it and see how hard you're getting stuck. And if you're getting really just stuck all the time, that means you probably have some prerequisites you need to learn first, and you can come back and try it later. For me, this was like about appropriate for my skill level. Yeah. I'm not technically an OS engineering student though. I am a random person. Okay. How do we check if the next descriptor is free? So we need to check the head and the tail. Give me a second to think. So So if they're equal together, so what I'm wondering about is, usually with ring buffers, at least the ones that I've seen, there's this kind of condition where the buffer is full if the one, like, it's like, so you push all these things, I think they usually reserve one slot of space. So the buffer is full if tail points right here. So tail points one past the end, right? And if tail is pointing here, then the buffer is full. That's my understanding of how this thing usually works. Otherwise, you can't disambiguate between an empty buffer and a full buffer. If you actually pushed every single slot here, tail would then bump to where head is, and it would look the same thing as an empty one. So my guess would be that the buffer is full if tail is pointing at head -1, basically. What's up, Ismail? Good to see you. That's my kind of approximate guess. I don't actually know if it says this anywhere. This is the location where software writes the first new descriptor. I want to collapse all of these things. Right. Receive and transmit. Packet transmission. Hardware tell, yeah, points one past loss. This was that thing about reading the head pointer. Apparently there are some race conditions involved with doing this. Okay, this is like some kind of detailed stuff. So I'm just going to make an attempt at this. But okay, but this seems important. Software can determine if a packet has been sent by setting the RS bit in the transmit descriptor command field. Checking the transmit descriptor DD bit in memory eliminates all descriptor data it's written to the IO bus prior to incrementing the head register, but a read of the head register could pass the data right. Updates to transmit descriptors using use the same iWrite path and follow all data writes. Okay, so there's some difference between accessing the registers and accessing the descriptors. Other potential conditions also prohibit software reading the head pointer. So the general strategy, I think, the first idea would just be to look at the tail pointer and see if it's equal, see if that plus 1 is the head pointer, which means it's full. But apparently we cannot read the head pointer because that's subject to a race condition or something like that. But if it wasn't for that, I would then I would implement it that way. If tail plus 1 is equal to head, then it's full. Otherwise, then we can fill out the descriptor here and point the pointer, like copy the data into the backing buffer, point the pointer at it, and then fill out any other fields that are necessary, and then advance the tail pointer while handling wraparound. Maybe I will just try to do that to make progress even if it's technically wrong. Okay. And so let's just start out nice and simple. UN32T. Yep, that's what I wanted. It's giving me so much code. I kind of want to turn this off, actually. I think it's giving me a bit too much. I don't really want to have it suggesting all this stuff to me. Can you stop until I ask for it, I guess. Okay. So we read the tail. This copilot is cracked. Yes. I don't know. Like a lot of this code is maybe wrong. If tail, so we need to handle wraparound, right? Static, I don't know. Or do int get index int 32t. I'm just gonna call it like position or something like that, and we're just going to return pos modulo k like num descriptors. So I think it was like 32 descriptors or something. So this is just going to do the modulo operation. So if get index tail plus 1 equal to head, right? Head. To actually access head. Okay. ring buffer is full. I don't know, return. To do what to do here. Okay. Then maybe we drop the data, I don't know. Otherwise, let's handle the happy case. Let's say, let's pretend, yeah, I need to think about concurrency, maybe. Like what, can this be called from multiple threads or something? I don't know. But just for the simplest case right now, let's just assume it can't be. In practice, it probably would be if multiple cores are doing network access at the same time. However, in this design of the kernel right now, there's kind of no concurrency actually in the kernel. There's a huge lock on everything right now. So it's more of a theoretical issue. I have 0 tools to help with race conditions. Yeah, I do not have any tools. Okay, otherwise, so what do we need to do? We need to look up the current descriptor, fill it out, and then increment TD, tail pointer. And so this should be fairly easy, I think, and even I think Copilot suggested this. Descriptors at tail. And then what do we, so we're trying to fill out this structure. And there's a bunch of stuff in here apparently, but maybe we can also look that up. The most important probably are the buffer and the length. So we can just start with that. No tools for race conditions. That's right. I'm not sure how I would do that. I know there's some user space tools. Yeah. Okay. So what we need to do is copy the data first off, and to do that we need to locate the buffer that the backing buffer that corresponds to the descriptor, and I don't know, just like, yeah. Get descriptor backing buffer. 32 T pause. And kind of want to assert a few things. Actually, you know what? I will make this an int. Ooh. So assert pause 0 and pause is less than k num descriptors, right? We want, this needs to be within the valid range. And this is going to return a pointer into this page we've reserved, basically. So in like this ultra stupid version of the driver I'm making, I just have a single page for the backing buffer for all of these. And each descriptor just gets like a fixed region within this larger backing buffer. And I'm just going to do something very simple, like size per descriptor is equal to size of GTX buffer divided by k num TX descriptors, something like that, which is going to be 4k, yeah, divided by 32. And then I'll just return GTX buffer plus pause times size per descriptor. So everything is static. I mean, honestly, even this is fixed. The size per descriptor is fixed. And that's a very useful constant actually that we're going to need to know. Okay, I don't know. Call it K backing. Descriptor backing buffer size. KTX backing buffer size divided by K num descriptors. Something like that. Descriptor. Yeah, the naming could totally be improved. These are kind of bad variable names. KTX backing. Like, this is all kind of ambiguous now. There's like this, maybe I'll call this total something. Wait, but this was not actually used. Okay, total, right? Okay, num TX descriptors. Whatever, I'll just keep it moving. Get descriptor. So then this is just, we don't need this anymore. This is just position times K. Backing buffer size. Super simple, right? And then over here, all we want to do is basically backing buffer. Man, the camel case versus snake case is, yeah, so inconsistent at the moment. So we get a pointer to the backing buffer, and then, I don't know, we mem copy something. From the given buffer, but what happens if it's too large or something? We probably need to return some error codes. At least for the moment, I don't know. I think if len is greater than k descriptor backing buffer size, I don't know, return -1, something like that. So now that we have that check out of the way, we can just mem copy from buffer into backing buffer len. It has been a while since I've done a mem copy from the kernel. How? String.h. Do I need to include something? Okay. Return -2, I don't know. So we need to include string.h. String.h. Discards const qualifier. Oh wait, okay, so wait, but I did this the wrong way, right? Destination source. Okay. Control reaches end of non-void function. Return 0. I don't know. Okay. So, we've copied, so we have a free, we've confirmed we have a free descriptor, kind of, because we checked that tail plus 1 is not equal to head, right? So for example, tail's right here, tail plus 1, you know, we still have some space, so or if say tail's right here, we're free to use it. If tail points right here, we're also free to use it. This is the last slot. If tail is right here, the buffer's full, actually, and we're just not going to use this thing, because otherwise we would populate it, increment tail, and now the queue would look empty. So we can fill out this thing, and we need to give it the physical address of the buffer. And I think, all right, John, thanks for all the help today. See you later. I think we can just use our padder macro for this, because I've just allocated that data as a global buffer in the kernel for the moment, which means that it's part of the kernel, and it should be within this region of the linear mapping that maps the first 256 gigs of memory or something like that. And the padder thing just, I believe it just simply adds the offset. It just adds the, or it rather subtracts the current base offset, because the pointer, the actual pointer value for this backing buffer thing is going to be a high memory kernel pointer, and we want to convert that to a physical address, which means subtracting the kernel base. Okay, descriptor len buffer length equals k descriptor backer buffering size. Okay, what else? do we have any more guidance on this? Maybe quickly look at the manual. So here is, yeah, the transmit descriptor legacy mode. To select legacy mode operation bit, blah, 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 should be set to 0, okay? Bit 29, it's like somewhere in the command. Should be written 0. So maybe also what I should do actually is 0 out the whole thing. Before I use it. So that'll be memset. The address is with 0, size of E1000TX descriptor. Yeah, so now we're zeroing out that entry, setting a few fields in it. If they have the RS bit in the command byte, then their DD field, so that's important. We need to do that, as written. So we need to at least be setting the RS bit, but time for a 20-second break. Stand up and stretch. Okay, check some offset. I don't really know what that is. Don't forget to drink water. That is so true. Command field, status field, reserved. Check some start, special. Okay. Command field. Okay. You know, it might be nice to have a structure for this also. Young people seem to put an awful lot of work and effort into breaks. That is true. That's true. Yeah, I sit around a lot, a bit too much, so I try to exercise my body and move around. Okay, so interrupt delay, VLAN packets. Report packet sent, report status. RS bit. When sent, needs to report the status information. This ability may be used by software that does in-memory checks of the descriptors to determine which ones are done and packets have been buffered in the transmit FIFO. Software does this by looking at the descriptor status byte and checking the descriptor done bit. Okay. When sent, defers writing the DD bit until the packet has been sent. It's used when the software must know that the packet has been sent and not just loaded to the transmit FIFO. When it has, okay, so this is kind of an option that affects this. This bit is reserved and should be programmed to 0 for all controls except this thing. Insert checksum, insert end of packet. Okay, one or many descriptors can be used to form a packet. Okay, I'm not totally sure about what to do there. Maybe I'll set it to yes. Just, okay, but first I will write a structure for this. Struct tx command. Well, you know what, actually, I don't know if that's necessary. These things are all just one bit anyway. So, with 8, t command, or rather, command equals RSV. Now we need to find this command. Yes. txd command blah 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 blah. Okay. txd command rs, for example. Command, I'm gonna set the end of packet just in case we need to. I don't think yeah. I don't really think I'm going to use that. Like insert checksum, I don't think I'm really using that. So that's what I'll do for now. Command. Back to this thing. Command status field. Is set. The status field is only present in cases where the rs set is set in the command field. In any case, that's a read, like a read-only part here. Okay, so that's cool. And the last thing to do would be to update TDT, right? 32 driver base TDT, and it's going to be get index tail +1, something like this. This code is probably pretty buggy. We're not handling this race thing well. But it was my attempt at writing a function to transmit a packet. now that we've, we're kind of handling the fullness thing here, maybe. I don't know the actual solution to this. It might have something to do with these DD bits, like this DD status thing. So how would this work? Maybe it's just helpful to look at this picture again. Or maybe I can read what this says. So we can determine if a packet was sent or not. Oh wait, but also, yeah, super. So the important thing was that these tail and heads are not byte offsets, but they are indices, and I think I'm actually handling that correctly. I'm treating them as indices into, yeah. Reading this register returns the value of head corresponding to descriptors already loaded into the output FIFO. Average of 4 descriptors per packet. Hardware fetches the descriptor indicated by the hardware head register. Right, so it's eating from the head basically, right? Tail points 1 past the last valid. Process of checking for completed packets is either scanning memory for write-backs or taking an interrupt. Other potential conditions also prohibit software reading the head pointer. So it's saying, if you want to see if a packet has been sent, don't check if it is behind the head pointer, basically is what it's saying. Update the transmit descriptors. So something along the lines of reading descriptors should be safe. So maybe the actual better solution is something like checking these DD bits. So let's just again pretend like we have a snapshot of the current system and tail is pointing here, and we're not sure what the state is. So currently we are checking tail and checking where it is in comparison to head, which involves reading head. So how would this work with the DD bits? Apparently we can check the DD bits. And so if head is pointing at something, its status bits should be cleared, because the status bits only get written back after the packet has been processed. Maybe I will copy this image over here so it's closer. So rather than reading the head register, what if we tried to just read the status bits of that descriptor? Because for all these ones that are in the buffer, they are owned by hardware and they should have empty status bits. By setting the RS bit, checking the transmit descriptor DD bit. Which is in the status. Shit. Okay. So basically, all of these things, but actually, wait a sec. So at the start state of this is fully empty. I'm not sure. Checking for 0 doesn't mean that much, actually. It could either be because it's currently in the queue, or we're just at the start and nothing has been filled in yet, which maybe that means these should all be initialized to have a DD set. Yeah, I think I'm getting kind of out of my league here, actually. I think this is actually a bit outside of the difficulty level I can do without like some guidance. So for the moment, I'm just going to keep my racy code here. And maybe it's time to ask AI. Open chat. Quick chat. What's a quick chat? Okay. Is the buffer size fixed? Currently, yes. It's always fixed for me. Okay. I'm just gonna see what AI says for the E1000. How do I check if the transmit descriptor ring is full? I was thinking of checking if the tail descriptor is one behind. Actually, there's a bug here too. I need to get index on the head, because what if the tail, what if the head's at the total start of this and the tail is totally at the end? That would also be full. I think I'm checking if the tail descriptor is one behind the head. The tail pointer is one behind the head pointer. However, the manual says this, which seems to say that reading the head pointer is prohibited from software. How might I do this full buffer check without reading the head pointer? It kind of is reading the wrong file, but so that's my current dilemma. But I think, okay. Is to use the DD bit, right? Maintain a shadow copy of which descriptors are in use. Check the DD to determine if the previous transmission is complete. Control / in the checkbox that you can select certain files. Thank you. Yeah, I would love to not use AI, but unfortunately I'm not smart enough. DD-bit is not set. That's the thing, is that true? That means we need to initialize all of these to have the DD-bit set, I think. We can try to imagine that. Yeah, we can try to imagine what this would look like. Maybe I will, 20-second break. I need to leave kind of soon, so I'll just kill that. So, okay, let's say we have four, right? And each of these can have a DD bit. And we have like a head, and a tail pointer. At the start of things, these are going to be the same. So here's how the algorithm currently works, super naive. So currently it's empty, and we're trying to push and add a packet. So currently we're like, okay, read both of them. If the index, if tail plus 1 is equal to head, then we're full and we bail out or something. Otherwise, this is free now. So we go and fill this in. And right, so tail plus 1, right, is over here. So we then like fill this in and then we bump tail. No, wait a sec, no. We fill in the current value of tail, right? We see that tail plus 1 is not equal to head. So therefore we fill in the current value and then bump this over. So now there's a packet in here. Let's imagine if the queue was full, which looks like this. This is a full queue because head points here, and tail's over here, which means tail incremented all the way over around, and tail plus 1 is going to be equal to head, so that's a full queue. Then let's say the hardware consumes one thing from the head. So now tail plus 1 is no longer equal to head, so we can feel free to populate this one, bump tail forward. And so now these 3 are full. That's how things currently work with the algorithm. The edge case might be that, let's say, tail head is here, and heads at the end. Tail +1 is not equal to head. I guess, wait, so head is actually always going to be constrained within these actually. So I'm not actually sure we need this. We only need it when we are doing these like something plus something, and we need to make sure to do the wraparound. Maybe wrap index is more appropriate. And unfortunately my, like, this thing is not working. Okay. So now let's imagine the like better way to do this, which is what AI is recommending. It's saying, so you simply look at tail and check if it doesn't have a DD bit, which means it's in use, by the hardware. Right, okay, and there's nothing to initialize there because, so in the, so let's say we're in the middle of transmission. Head points here, DD is 0, DD is 0, because we added a bunch of stuff here, right? And maybe just like over here. And let's say it's all default initialized. Right, if it's all default initialized to 0, we're going to think everything is full. So I think that's why we need to default initialize everything to 1. Possibly. So if everything is default initialized to 1, from the perspective of the tail pointer and from this function we're writing, we're just trying to find a free descriptor, and if a descriptor has been processed, it's going to have a 1. And so let's imagine this scenario happened. We're looking for a free space. We just check, is the current one free? And if it is, we put a packet in there and then bump over. And now hardware is processing this. So that's kind of simple. We're just checking if the current one has been processed already. So then let's say the hardware processes it. So now it's going to mark a 1 here, right? So basically here, all we're doing is we're checking if the current 1 is empty, basically, which means it should have a 1 there. So which means, we should initialize everything into 1. On the initial state, everything's initialized to 1, and because if it was 0, we would think everything's full. And so I'm just going to implement this, I think. Does command, okay, command. Unit 8T. This is kind of a basic question actually, but wait, when you do these bit operations, it like 0 fills in the rest of the bits, right? Pretty sure. Okay, so I'm just going to stage this. I mean, we could even try to see if this like works. I worked in circles, and there's always this design. Just how do you decide if the queue is full or empty with modular on the head or tail? Yeah. So I think we sort of have this plan to implement the full buffer check in a race-free way. And it's not really that hard, actually. It's just you need to default initialize all the descriptors to have a 1-bit to make it look like they've been processed by hardware. And then from there on, you can just simply check if the tail is currently pointing at an empty descriptor and simply use it. Before I do that, I do need to go. But can I just run something quickly? Try transmitting a few packets by directly calling your transmit function from the kernel. You don't have to create packets that conform to any particular network protocol. Run this to run your test. You should see something like blah blah blah. Let's just quickly do that, and then I will head out. Okay. I'm just going to do this directly from here. We're going to do E1000 transmit. We're going to take the pointer to the G, and then we need to pass a buffer and this thing. And actually, no, I'll make it way less. I'll just make it something like 8. And then I'll just make a buff. I don't know. Maybe I'll just make a buff of length 8 and then copy into buff B 8, right? And then just transmit this buffer, for example. Maybe I'll do that a few times. I don't know. Am I doing this right? Okay, I don't know what's going to happen, but and then my function. So this is actually possibly a public function, which means it should be in the header file. And this const does not need to be here then. Okay. Implicit function declaration. What? Why? Okay, I guess there's something wrong with my headers. I don't know why. Okay, does this work? Unknown type E1000 driver. What? It's declared right here. 21, right? From the header file. Ah, okay. Okay, so that means this type needs to also be in here. That's fine. Probably even. Okay, I don't know what's going on, but let's just run this. And okay, so what do we see? We see each line gives the index, the buffer address of the transmit descriptor 012. The command CSO length fields and special. If QEMU doesn't print the values you expected, so what do we expect? We have some addresses of buffers, and we have some fields. And the command has the RS bit set. Wait. Length. We are setting the length, right? It's a 16-bit. Okay, it looks a little bit weird, but I gotta go. We're gonna look into this next time and figure out what's going on, but at least we got something sketched out today. We got the NIC kind of finished initializing basically, and we have a sketched out routine for how to actually send a packet. So thanks a lot for being here, and I will see you next week. Peace, have a nice one. Later.